Greetings, students of organic. Are you ready to shift into the carbonyl land? So we've been doing a lot of reactions with aromatic systems, and our functional group theme for the next several weeks will have a carbonyl. And so, of course, this is all working toward a big picture. Nothing is going away. And in fact, we have used carbonyls before in reactions, only they were usually the product. So I was back in Organic 1, and we'll review some of the really popular ones that you'll have to be expected to recall and understand to proceed with this chapter. But we have not very often had carbonyls as the starting material. There's only one reaction that was really focused on where we did that, and that was the Grignard, which we'll review again. Shows up again in this section. So in order to start off the carbonyls, we're going to narrow our focus. Remember, carbonyls are in a lot of functional groups. They are in, so carbonyl is that carbon-oxygen double bond, right? And that's itself is not a functional group, that's a bond. And the carbon-oxygen double bond is found in amides, it's found in carboxylic acids, it's found in aldehydes and ketones, and acid chlorides, acid anhydrides. And don't worry, we will get to those, but to kind of keep it simple, we start with two that have similar reactivity, and that would be aldehydes and ketones. And that's what this section is about. That's where our focus will be narrowed until we are ready to expand it. So in the old days, when they were trying to decide and determine if a structure had an aldehyde present, they used to do a qualitative test called the Tollens test. And that was because spectroscopy wasn't available. Now it would be easy. We'd do an NMR and we'd see around 11 ppm, that really characteristic aldehyde peak. And this would be proton NMR, right? The aldehyde proton peak. Or even a carbon NMR would give us that nice carbonyl distinctive peak at 200. Or even an IR, we'd get that carbonyl stretch. However, pre-spectroscopic times, they had to rely on knowing how they react and what they look like when they react. And aldehydes underwent a very specific oxidation. So notice if you have a generic aldehyde, you can oxidize it with an oxidizing agent to have another bond to oxygen to make essentially carboxylate, a carboxylic acid that's been deprotonated. And then in doing so, the oxidizing agent gets reduced. And notice that in this case, our oxidizing agent, which we often abbreviate, we're going to encounter a lot of oxidizing agents soon. We abbreviate with the O in brackets to indicate that's the oxidizer. It gets reduced to silver 0, elemental silver, which drops out of solution. And I'm pointing this particular one out because it's got kind of a nice looking result. It's one I actually enjoy doing when I can get my hands wet in the lab. And I've had some students help with it as well. And I kind of like to use them as like a little trophy or something, you know. So we see these, they look like little chemist trophies, right? You see the silver plated Erlenmeyer used to be something you could see right through, transparent. Now you can actually see, in this case, my reflection. I love to do this one in person too, when the chance arises. So that's a fun demo. So that's a silver plated, basically, mirror along the glassware. So that test was proof, if you saw that silver deposit, that an aldehyde was indeed in the solution. So it's kind of a fun test. But we don't have to do that anymore. It's worth knowing those sorts of things, but we have spectroscopy to tell us that, which is a lot less work than doing a series of tests, because it still doesn't tell us much about the structure other than one functional group that's present. Since we are starting to focus on a functional group, we're going to go into how we name them. First, we'll do ketones, then we'll do aldehydes. So ketones, you might have actually already known this because we talk about acetone all the time if we're thinking about lab-related stuff like washing glassware and stuff, or in everyday life, acetone is found at Home Depot, for example. So -one is the suffix that indicates that a ketone is present, and you replace that E that was an alkane, so like hexanone instead of hexane, right? But if the ketone's a substituent, it's not part of the parent, not the main chain, then it's got the oxo prefix. So let's kind of do one of each of these so we could see what that looks like. So you can go practice some more naming on your own. Now, if we take a look at this, here's one that's cyclic. Ketone is higher priority than alkene, and that's because, remember, the oxidized functional groups have higher priority than the less oxidized. So those oxygen-containing functional groups are way there, up there at the top. So we're going to give the ketone carbon number 1. Then we're going to number around the ring such that the next functional group gets the lowest number. So we're not going to go this way. We're going to go this way, 2, 3, 4, 5, 6. Okay, so we have a 6-membered ring. So we have hex. We have an alkene. So we don't have a hexane, we have a hexene. And then I'm not going to have the E there. I'm dropping the E because our suffix is -one. We're not a hexene. Don't forget the cyclo because it's not linear. And then where is my ketone? It was number 1. That's implied. We don't have to put it there. We could put ene 1 -one, but so that would be a synonym for this. But we also have to tell everyone where the ene is because that was lower priority and that is not number 1. So that was at number 2. We have an alkene at number 2, 2-cyclohexene-one. An appropriate synonym would be cyclohex-2-ene-1-one. And that's extremely thorough, just a little longer in a mouthful. So the more common way to opt, what most chemists would opt for is the 2-cyclohexenone. It's a little more efficient, but it's nothing wrong with getting with overdoing it. You don't want to underdo it though, right? So cyclohex-2-ene-1-one would be fine as well. Okay, let's do another one. Now, carboxylic acids are higher, have more oxidation, so 3 bonds to oxygen versus 2, so they're going to get the higher priority. And so we have that list too that you could refer to. So we're going to give that carbon 1, 2, 3, 4. So our parent name is going to be bute. We have no alkenes, no alkynes, so that we get an "and" for our infix. We have if you look at the chart, since this is the highest priority, it gets the suffix. So since the ketone was not the highest priority, we get a chance to use the prefix on that one. Okay, so for carboxylic acid, it's oic acid for suffix, butanoic acid. And then the prefix for ketone is oxo. So we say oxo. So it's at the 3 position, 3-oxo-butanoic acid. So it's implied that the butanoic, the oic part, is at 1. And whatever is lower priority than that gets the number, so 3. Okay, let's try some aldehydes now. Put that there in case you didn't read it. Okay. Aldehydes. They, once again, you drop the E if they are the highest priority group. New suffix, al. Don't confuse that with all. You have to listen carefully because hexanal sounds a lot like hexanol. Hexanal. If it's the substituent, so not embedded in the parent chain, or it's not the highest priority, then it's formal, which comes from the whole formic acid, which Latin forma ants. I guess the formic acid is found in the venom of ants. That's not, they're not like entirely toxic, but they can have a little sting in their bite, and so that's what's found in ants. So that's where that old school naming system comes from for giving this, because you look at formal and you say, how does that relate to a aldehyde at all? And that's because formic acid, which is the aldehyde on one side, acid on the other, this is formic acid. That's found in ants, and then the forma from the Latin for ants gives it that name. So all the old school some of the old-fashioned history kind of makes its way into this naming system. It's kind of interesting. Okay, so this has multiple things going on. First, let's stick to the same plan though. 1, find the longest carbon chain and figure out how to number it. So you do that by finding the highest priority group, which is always the most oxidized carbon, which is this one, right? So we're going to give that one 1. And then we go 2, 3, 4, 5, 6. Oops, it's cutting me off there. There we go. So we're going to have a hex parent. No alkynes or alkenes, so it's a hexane parent. Our highest priority group is an aldehyde, so it's an hexanal. And now we get to name substituents. We have a methyl at 3, a bromo at 4. That just goes in ABC order. Bromo comes before methyl, B before M. It's not numeric order, it's ABC order. So we name that accordingly. 4 bromo, and this is where it gets interesting to see if I wrote, get myself enough room. 3 methyl, squished. There we go, hexanal. That dash didn't have to be there, but I put it there just kind of for clarity. Okay. Let's do an aromatic ring. Just to kind of combine the old with the new from the last section. So highest priority group, a carboxylic acid versus an aldehyde, we know that. But since we have an aromatic ring, and we know these are substituents off the ring, let's try to find one of those like classic chunks that make up the ring. You know, those common names, you know, like anisole and whatnot. So this, for example, is benzoic acid. So I'll write that down. And this is benzaldehyde. So who is the, so you try to get your circle as fat as possible so that you have as little substituents to add on. Now, benzaldehyde would imply that the benzaldehyde is part of the parent, right? And the benzoic acid would imply that the carboxylic acid is part of the parent. So who wins, the blue circle or the black? Well, since carboxylic acids have higher priority over aldehydes, we are going to let the parent be benzoic acid. But then we're going to name the substituent relative to it. So we're going to give that a carbon 1, and then 2, because that's the next lowest number we can give that one. And that's an aldehyde. And that's, since it's a substituent, we're going to call it formal. So at the 2 position, we have a formal group. 2 formal benzoic acid. So, you know, the naming's very systematic and predictable, but sometimes you kind of have to figure out those little gray areas. So that can only really be overcome with practice. So try a bunch more in the homework. I'm going to move on to reactions now. That's the fun part. And in order to move on, I feel like we're going to need to do some review. I'm going to leave that at the top just in case you need to copy. We're going to need to do some review because there is a lot of reactions that are going to be assumed knowledge, and this is back from Organic 1. So it would be good to stop and just answer these. Not going to do every mechanism because we have done this. And we don't spend the second semester repeating the first semester mechanisms in great detail. But let's review. And why are we doing this? These are ways to get to the same functional groups in this chapter, aldehydes and ketones. Okay, so organic, this whole page. And if they are not familiar to you, that'll give you kind of a pinpoint of where to go study a little bit so that you feel comfortable when we put it all together in a synthesis problem. Okay, so PCC, remember that's our gentle oxidizer. It adds more bonds to oxygen, but it stops at aldehyde. So we get a primary alcohol, we can go to an aldehyde. However, if we want to keep oxidizing, instead of having just 2 bonds to oxygen, we want to have 3, like a carboxylic acid would have, because you can see that degree of freedom still there to add another one. We would need something stronger. Remember, this is called the Jones reagent. So primary goes all the way to carboxylic acid with the Jones reagent, much stronger oxidizer. Now, if we're starting with the secondary alcohol, then we can only, at most, make another bond to oxygen, 2 at the max. Otherwise, we'd have to cut off in our group, and that's not going to happen. So no matter what you start with, you could have PCC or Jones, we're going to have a ketone. And I like to write out the functional groups because sometimes just writing the word along with the structure and kind of trigger the right association in your brain for the future. It don't work for me, so I gotta share that. Okay, this is funny. This is copied and pasted from my 211, my Organic 1 notes, but I have that same typo. Tertiary alcohol needs that extra R group there, right? So we're gonna have no reaction because in order to further oxidize a tertiary alcohol, you had to lose one of these R groups, and Jones is not capable of doing that, and neither is PCC. Okay, some more to consider. We can arrive at aldehydes and ketones from alkynes. That was a huge section in Organic 1. So if we have a terminal alkyne, I'm going to do 2 scenarios. So hold on, let me remind us that we always kind of notice that we have a terminal or internal alkyne. Okay, so there's 2 active carbons on the terminal alkyne. You have carbon 1 and 2. All right, so if you subject it to sulfuric acid in the presence of H2O, or also sometimes mercuric acid is HgSO4, those are synonymous, you will get a ketone. It looks very strange because there's no alcohol there to begin with, but the mechanism, as usual, explains it all. And I'm not doing the whole mechanism, but it's something you might want to review. I'm going to show, just grab the key step out of there. And the key step was that eventually you arrived at an enol. How'd you get the enol? Markovnikov addition of water across 1 pi bond. I hope that all sounds familiar. Markovnikov addition of water. What does that mean? That means that we add an H and an OH, in which the OH goes to the more substituted carbon, the H goes to the less substituted carbon, and it only happened 1 time because we arrived at an enol. What do enols do? Tautomerize. Don't let those enols sit there, they tautomerize to the keto form. That's a classic reaction that the tautomerization that we need to recognize. So it's worth reviewing because I know it doesn't look straightforward. You could take the same terminal alkyne and do the opposite. So this was Markovnikov. Let's write that down too. Markovnikov addition of H and OH. It's a hydration, water, right? What if we do anti-Markovnikov? Remember, that's what borane does. Anti. You get the exact opposite. How does that look? That looks like, oops, an aldehyde. What? How does that look like an aldehyde? It's actually the most obvious thing, in my opinion, is the opposite key mechanistic step. Because looking straight at this, it's a couple steps forward in logic. It's hard to see that connection right away, how the aldehyde is the opposite of the ketone. Let's look at that key mechanistic step where we get to the enol. Anti-Markovnikov addition of H and OH to carbons 1 and 2. So in other words, anti-Markovnikov means that the OH goes to the less substituted carbon. Carbon 1 gets OH. Carbon 2 gets H. Let's draw that out. So I'm drawing the H. I'm actually going to number these carbons again. And new H on 1. Okay. Still got a pi bond. New, oops, I did it the wrong way. New OH on 1 because it's anti-Markovnikov. New H on 2. Anti-Markovnikov means hydrogen goes to where there's less hydrogens. New group goes to where it's less substituted. Remember Markovnikov's rule? So anti-Markovnikov addition of H and OH. And I also love just doing this one key step because we are in a carbonyl section, which means tautomerization is coming back with a vengeance in this class. So if this was a tough point for you previously, kind of nail it down while you can. Tautomerize. Okay, so That's how it looks opposite. How, when we tautomerize this enol, the one that has the OH over here, notice the carbons 1 and 2. Let's number them again. 1 and 2. 1 and 2. So when carbon 1 gets the carbonyl, it's on the end. It's an aldehyde. When carbon 2 gets the carbonyl, it's in the middle. It's a ketone. Makes more sense when you see that middle missing piece of the mechanism. That's why we do mechanisms, right? Okay. Last reaction that you want to be able to pull out quickly from 211 or organic 1, whatever you called it when you took it, is ozonolysis. Don't worry, this one's a student favorite because look at, we get to do that. Oxidative cleavage, you get 2 from 1. So unless it's connected, of course. Those are fun. R2, R4, R3. So let's write that out. Oxidative cleavage. Okay. All right. I feel like sometimes that Markovnikov thing is not always fresh. I'm going to write one more clarification here. Okay. So just to remind you, good old Markovnikov, his rule that he's famous for and he got named after, basically just means new group on more substituted carbon. So that means if you're not following Markovnikov's rule, if you're anti-Markovnikov, that means the new group, in this case water, not BH, on less substituted carbon. So whatever the nucleophile was, or whatever it was other than H usually, is on the less substituted carbon. All right, that was review. Are we ready for some new stuff, I hope? And remember some of these review concepts. Notice what we were doing. We were making ketones and aldehydes. Now we are going to put them at the beginning and react them. So mechanisms stop us from getting overwhelmed with memorizing. They give us the logic behind it, and you're going to see a lot of carbonyl reactions over the next several weeks, a lot. And at least for the ketones and aldehydes, they're going to follow two, for the most part, main mechanisms that fall into one of these two categories. And when you can see that they can be simplified into one of those two approaches, I think it's kind of a game changer there. So, in other words, when we have a carbonyl and a nucleophile, you're going to pick one of two mechanisms. So remember that carbonyls have a polar bond, right? We're going to rely on a lot that we know from our structural study of these compounds way back in the beginning. So if we draw the dipole here, we have a delta plus, a delta minus. So of course a nucleophile that's sufficiently strong is going to be attracted right there, right? So when that arrow gets to go is dictated by the reaction conditions. So we're either going to have basic conditions, and pH paper is basic when it's blue, so I like to do blue for basic. Or we're going to have acidic conditions, so pH paper is red. So I'm going to try to stick to a little bit more red. Oops. Acidic. Acidic. Okay, so if there's no acid present, in other words, we have just a plain old nucleophile, usually a minus charge there even, because it's a basic condition. So let's add that in. And then there's always a water workup just to neutralize it, because you end up with a minus when you have basic conditions. So we neutralize it, and that's not usually, that's even not always shown, but to be tidy and clean and thorough, we'll probably show it. But the main business kind of happened in the first step. So in basic conditions, we're going to do what's called 3 major steps: attack, open, protonate. Attack makes sense. That's what nucleophiles do. Why is it going to attack? Well, look at this thing here. We have a delta plus and a delta minus. Attack. Open. Open the pi bond. Let's write those words out. Attack. Attack the delta plus of the carbonyl carbon. Open the pi bond. All right, let's draw what that looks like as an intermediate. R group's all still there. We have tetrahedral intermediate. Notice it was trigonal planar. Now it's tetrahedral. New group attacked on that bottom spot there, nucleophile. And we also have an O minus because we opened the pi bond, gave the electrons to the oxygen. Last step is step 2, protonate. So water comes in and protonate. This is a simple acid-base neutralization step. Nothing fancy there. So notice what we get. Tetrahedral, new group, OH. Okay, so let's even, it doesn't have to be symmetric. Let's even put a prime on here, R prime. All right, so we're going to write that out. Attack, open, protonate. Put a nice red box around it. Oh, well, I guess we're going to do red in the next section. Put a blue box around it. Attack, open, protonate. Okay, AOP. I might even write that over here. When it's basic, we'll do AOP. That's going to be the mechanism. We're going to do the same steps. Look over the arrow, you see carbonyl. Look over the arrow, you see basic conditions. What's a basic condition? A nucleophile that's negatively charged usually. Step 2 has water to neutralize it. That's a dead giveaway that it's basic to begin with. Attack, open, protonate. Okay. However, we are often going to see, especially throughout this class, when we are presented with a basic option, we are going to be presented with an acidic option. So we are always going to ask, if this is what happens when it's basic, what's going to happen at low pH when it's acidic? And this is the answer. Different mechanism because acid is not nucleophilic, not a good nucleophile. But you can turn it into a situation where it can make the electrophile more reactive. Who's the electrophile? The carbonyl. All right, so notice there's a clue. These lone pairs have been drawn in. We have an acid. What are the lone pairs going to do with the acid? They are going to grab a proton, right? So let's grab a proton. Making this as generic as possible simply because there's going to be a lot of variable reagents over there to give us different looking functional groups. I'm also going to draw the end product. We're going to get the same thing. Let's put R prime here just so it looks the same. We're going to get alcohol 2 ways with a new group. What's the new group? It depends on what you want. So the new group is the nucleophile is actually not negatively charged here. It's neutral, but we're in acidic conditions. So first step was protonate. But this protonation step has its own name because what we're doing is we're activating the carbonyl. We're making it more reactive. I'll go back and explain that in a second because that's a very important step. We'll see why in a minute. Notice how this is positively charged now. An otherwise weak nucleophile is much more eager to attack now than it was before. Why? So here's our weak nucleophile. So if it's a nucleophile, it presumably has like a lone pair or something, right? Now, it is much more willing to attack because oxygen says, thank you, I get my electrons back, right? So it's activated. I'm going to write that down. All right, so protonate to activate. So you're going to hear that phrase a lot in the next month as we cover carbonyls. We're going to say activate the carbonyl first. That's because acid's present. That means find the proton and get it on the carbonyl before you attack. So this is what we're doing. We're activating this carbonyl. Now it's ready to be attacked. Okay, so then, because before this was not a sufficiently strong enough nucleophile to attack this on its own. So to make this more reactive, activate it, then now it's ready for attack. So this step is attack. Now let's draw that in. Oops, I already drew a double bond. OH. Notice how when we kicked it open, we don't have an O- because it's already been protonated. Tetrahedral intermediate. Nucleophile has an H still. So that's the thing that needs to be neutralized. Acidic conditions have positive charges present. In general, basic conditions have negative charges present. So you know you're doing the mechanism correctly if you're matching that theme, right? Should not have negative charges in acidic conditions for the most part. Otherwise, they just wouldn't exist. They'd get it eaten up right away by another proton around. So now we need to neutralize. So let's do this. Whatever the conjugate base is of your acid. So your acid was HA, so A minus. So conjugate base of acid. All right, here we go. Come neutralize our product. So we're deprotonating. Sometimes you're going to see steps abbreviated. We're going to be so many mechanisms that you're going to start seeing minus H plus, and maybe the arrows won't be shown, especially in your answer keys. So, for now, draw it all out. But as we practice more and more and more and more, if you're doing it just for practice, it's actually okay to shorten it that way. Okay, so how would I summarize what happened here? First, we activate. Then we attack. Open. Deprotonate. Those are the same steps. This list is going to be consistent throughout most of this chapter, unless we have kind of an unusual mechanism with transition metals and whatnot, which we do have some of those. All right, so what are these variables here? So this is a very generic template, but it's time to define some of these. We're going to have a list of what can be a nucleophile, okay? And so let's take a look. We could have water. We could have alcohol. We could have even a diol is actually quite common, that particular diol. We could have sulfur. We can have thiol. And you know what? I don't focus on this one too much, but that one's possible too. So just in case it's not impossible, but my bigger focus will be on the diol. Nitrogen nucleophiles will have very similar amines that are primary, and then secondary. Won't have tertiary because we can't neutralize that. Hydrogen nucleophiles will have aluminum hydride like LAH, sodium borohydride, and then that's probably the main ones for now. And then for carbon nucleophiles, we'll have one that's familiar, Grignard, but we'll also have nitrile, and a really unusual looking one, the Wittig reaction. But this is just a little preview of what's to come, so hopefully it won't look too familiar. Here's our negative charge on the carbon. So that list is basically going to organize everything that we will see from this point on. So, oxygen nucleophiles. We're going to start there with that. See how we're going in order? Oxygen. And then sulfur is really analogous, but we're going to start with oxygen. So hydration means we're adding water, right? That's what hydration means. So let's try some of these. All right, so if we add water to a ketone, and then we have an acid catalyst. So it could be H+. A favorite organic acid is tosic acid. What is tosic acid? Let's review that real quick because you're going to see a lot of it. Tosic acid means you have a toluene, hence the tos part. Tolulyl sulfonic. That's the tosol. So you take like sulfuric acid's Lewis structure, and then instead of one of the OHs on the left, it's an O toluene. So there's the acidic proton there. It's abbreviated TSOH. It is not TS plus OH minus, which is a common misconception. It is the opposite of that. It's not base, it's an acid. So if anything, it's TSO minus H plus. See that? So this is the TSO minus and the H plus. All right, so sulfuric acid could also be another one for the acid catalyst. So what we'll do is notice whenever we have an acid catalyst mixed with water, the acid present in the mechanism is H3O+. So when you're writing your mechanism all full and proper, we use H3O+. And we're going to do our lone pairs. Acid conditions, what do? Activate first. Acid, activate. Activate the carbonyl. Okay. Carbonyl is activated. Why did we activate it? It's activated for attack. Who can attack? Look over the arrow. Not the acid. Water is the only nucleophile possible. Kind of a hint was that this is called a hydration reaction, which meant it's going to be hydrated. Here comes water. Attack. Open. OH, R. Now here we have our water oxonium ion that needs to be deprotonated. So neutralize, deprotonate, the D step. Who can deprotonate? The conjugate base of H3O+. H3O+'s conjugate base is more water. Neutralize. So now we have, I'm going to just clean this up a little. R and R, put those on the same side. OH and OH. So one O came from the carbonyl. The new O came from the water. So we have two OHs on the same carbon. There's a special word for that. Twin OHs, they have the same mom or dad, same parent carbon. So they're the Gemini, geminal diol. It's also sometimes called the hydrate. So the hydrate of that carbonyl would mean that water was added. So that it means you had a carbonyl that became hydrated. How do we see that it was hydrated? Where did the new water come in? Well, look at that. H2O right there, the hydrate. Okay, but you should be able to name that as a hydrate or geminal diol. Now, we will see this pattern where we have those two mechanisms possible. Because we could do it in acidic conditions, we can often do it in basic conditions. You're going to love basic conditions, by the way. So much shorter, because we had activate first, which is not present in basic conditions, then attack open, then deprotonate to neutralize. Let's see if we can remember our basic conditions. So basic is take our strongest nucleophile present, not the water. The water's there to neutralize later. Okay. So notice it's not shown in 2 steps. That's not it. So it can be. Sometimes the second workup step won't always be explicitly shown. So you can just assume we want a neutral product at the end. Kind of be flexible with that. Attack right away. No activate. Strong enough. Hydroxide is a strong enough nucleophile to not sit around waiting for activation. So you don't have it wouldn't work in acidic conditions anyways, right? So just turn into water. Attack open. Okay, we have R, new OH. Old O becomes O minus. Used to be carbonyl. Okay, now protonate. Attack open protonate, AOP. So I'm going to clean that up and put them on the same side just for clarity so we can really see it's truly another geminal diol. 2 ways to get a geminal diol, acid conditions or basic conditions. Why do we need 2 ways? It's annoying to say, oh, why can't I just learn one? Why do I have to learn double? It's a gift, really, because later when we're working with bigger compounds, let's suppose you had to make a pharmaceutical drug, which is inherently way bigger, and there's a base-sensitive functional group, but you need to make a hydrate out of that carbonyl. You can't use base. Thank goodness you could use acid, right? You have the option. So most functional groups are considered acid-sensitive or base-sensitive, and then you have to find a workaround for it. And so having those 2 options gives you more tools to work around it. All right, so another geminal diol. So these hydrates, it's kind of interesting because it's really an equilibrium. We're in an acid-base situation. So let's draw out all the hydrates. We're not going to draw the mechanism for each case. So for formaldehyde, the hydrate, which is the aldehyde that has no other group on it, just 1 carbon. The hydrate with 1 carbon would have, there's our geminal diol. For acetaldehyde, 2 carbons. And then for acetone, oops, we need to leave our H there. So this is really an equilibrium. And what's interesting is that the equilibrium favors one direction or the other to a different extent depending on what's attached. So for example, for formaldehyde, it's almost all the way forward. So you can just consider that reaction going completely, 99% diol. However, it drops a lot when you add a carbon chain, only about 60% diol. And now, with plain old water here, we have only about 2% diol. So the fact that we have, what's actually changing? Let's circle the change. So we replaced this H with a methyl here. And then we kept the methyl, but notice that the H has stayed the same here, but we have a methyl there. So in other words, we could say this has 2 electron donating groups. This has 1 electron donating group. That's what methyls are, right? And this has 0 electron donating groups. Why does increasing electron donating groups decrease the reactivity? I'm gonna write that up here. Whoa, where did you go? Come back. And I don't know what that shortcut was. That might be useful someday. Okay, so increasing electron donating groups on carbonyl decreases its reactivity. So what that means is that aldehydes, which have only 1 R group max, therefore reactivity of aldehydes, remember aldehydes have this general structure, is greater, only one electron donating group, than the reactivity of ketones. We're going to take advantage of that many times, that trend. But why is that true? Look at what happens when we have a carbonyl with an electron donating group on there. Electron donating means we're giving electron density that way. What happens to that delta plus? That delta plus gets diminished, right? Gets smaller. So it's effectively a teeny tiny delta plus. That means the nucleophile coming along is not so attracted to that teeny tiny delta plus as it would be if there was no electron donating group present, right? So in other words, I could draw a bigger delta plus on this one compared to a smaller delta plus there. The nucleophile would pick the aldehyde over the ketone any day. Okay, so that's going to be an important trend we'll watch out for. And we could take advantage of that. We could say, hey, let's make it even more extreme. Hydrogen does nothing. Let's add an electron withdrawing group. Chloral has just that attached, EWG. Taking electron density away, making this delta plus nice and fat. Water is attracted to it. So you're not going to be asked specifically, oh, what numbers, but you can be asked a comparison question, right? And we can predict that. So CCl3, we're going to make our hydrate, geminal diol. Now, the question is, do you expect the equilibrium constant for the hydration of chloral to be greater or less than the equilibrium constant for the hydration of acetaldehyde? Acetaldehyde was the middle one. So in other words, would it be greater than or less than 60% diol? You thinking about it? Well, it's electron withdrawing, more reactive. Electron withdrawing is going to definitely be more reactive than electron donating. So definitely more than 60%, right? All the way. So comparisons are the kind of thing, not the numbers, kind of keep the trends in mind. Okay, so we've learned time and time again that when we can use water, we can also substitute it with alcohol. So in previous reactions, we might have had water, and then that would make an alcohol product. If we used alcohol, we get an ether product. Can we do the same here? So look at this. All we're changing is we're doing a little different R group, but we have an aldehyde. We have tosic acid. Here's our acid catalyst. And instead of water, we have methanol. ROH instead of HOH. Well, guess what? Yes, it works, but we won't get a geminal diol because we don't have the alcohol OH to add. We're getting rid of the H at the end. So what will that look like? We keep the R group, not the H. So here's the OH from the carbonyl. Here's the O from our nucleophile, methanol. But we get to keep the methyl, not the H. Why? If that's not clear, we'll see the mechanism. Notice it's not two of the same groups. It's not geminal diol. So we have a stereocenter now. So watch out for that. It's going to be racemic. Okay, let's show why we do not get a geminal diol. Mechanism proves it all. We are in acidic conditions, tosic acid. Tosic acid mixed with water is H3O+. So tosic acid mixed with alcohol is R, right? OH2+. So in other words, draw out your alcohol. I'm just going to call it Me, just make it short for the mechanism, methanol, but protonated. There's your acid for the pot, because tosic acid mixed with methanol doesn't sit there. Those react. Those make the new acid for the reaction. Okay, activate. We are in acidic conditions. We always activate first. Activate means protonate that carbonyl, so it's ready, even more reactive than it was before. Activate first. Now it's activated. It wants to be attacked. It will relieve that positive charge on oxygen. Who's going to attack? Look over the arrow again. Toxic acid's never your nucleophile. Water or alcohol? We have no water. We've moved on. Alcohol. So I'm going to call that MEOH just to kind of keep it clean. Attack, open. Here we go to from our trigonal planar intermediate to our tetrahedral. OH, H, ethyl. Those were always original atoms. Of course, the H on the OH is new from the protonate, the activation. New group. Bond is to O. Bond it to O. O has what attached? Everything with it. The H is still there. The methyl is still there. Hence, it is positively charged. Okay? Neutralize time. More methanol comes along, just like more water would have. Neutralize, deprotonate. Take us home. Okay? Okay, so this is called not a hydrate because we didn't add water. It is not called the geminal diol because we don't have two alcohols, but it has a name. It's called a hemiacetal. Hemi, like in halfway, to an acetal. So what's a full acetal, you ask? Like, no, I didn't. Actually, it's a good thing to ask because biochemically speaking, extremely relevant. We'll see soon. Means it's not done. It can actually keep reacting if there's sufficient time or reagent present. So because it says excess, we're going to assume we have plenty of that protonated methanol around. So to redraw your methanol, well, let's even just draw Me just to keep it, like I said, as clean and easy to see as possible. MEOH, but it's been protonated by tosic acid, and it can react again. So we take this guy. Who's going to react with? Well, we're going to show how hemiacetal could become full acetal. So if this is halfway to an acetal, which means one ether, one OH, you can predict that if we convert the other OH into an ether, that's our full acetal. So in other words, this is our goal. Whatever your original R group was, that ethyl, our aldehyde proton there, our first ether that we made, and then replace the other oxygen with our second ether. That's a full-blown acetal. So this is the goal. How are we going to show that? We got to replace that OH with an OR. So OR. That means the OH needs to go. And the most common way to make OH go is turn it into water. So let's do that. All right, so hemiacetal, OCH3, OH2 plus, good progress, it's ready to go. Now, we are ready to get that water to leave. There's a couple ways we could do it. We could just let it leave, make a carbocation SN1 style. But you know, carbocations are pretty high energy, and what's actually more common is to go ahead and push these electrons down and kick that off. We'd rather have a positive charge on oxygen because that's still a full octet than a carbocation if possible. But it is one of the resonance structures. If you draw a resonance structure, it's the carbocation. So I actually do accept both. Just wanted to let you know that this is why the reasoning why we do that. So here we have the OCH3 plus. And there's another reason we do that. What does it look like now? Let's zoom in a little. So see what I did there? I'm going to pause for a minute because that was an important step. I want that water to leave. Instead of just having it leave and having a carbocation, I encouraged it to leave by using these electrons to push through and make this pi bond, ejecting it out. This looks like an activated carbonyl now, right? So there's a reason I did that. It looks like an activated carbonyl. What happens to activated carbonyls? They get attacked by more nucleophile. Who's our nucleophile? That's dependent on the reaction. This reaction is methanol. Here it comes. Remember, that's what we want, right? Because we're trying to get to that acetal. Has an OMe there. And right now we only have one OMe. We need two OMe's. The other OMe has to come from methanol. Attack, open. We're getting so close. Okay. Ethyl that's always there, proton that was always there, old OMe, new OMe from the new methanol, second methanol, but still has the H attached, therefore it's positively charged because we're showing the full mechanism. But notice how long these mechanisms are getting. We're going to, after lots of practice, take advantage of the fact that you're going to be able to drop that soon. So because I've shown that deprotonation step many times, you may do that if you understand it, minus H plus. How did that happen? Go back to the previous mechanism and make sure you can walk through that. You're going to see that happen more and more in your solution manual or solution guide for our work too. Okay, so acid base is an assumed mechanistic understanding. All right, so minus H plus happened there. Boy, that is the first time I've done that today, and it seems to be easier to do. See how much more we have to cover? Don't worry, I'm not doing it all right now. Okay. All right, so these are important functional group names. I'm going to put them in here again. Halfway through, we made our hemiacetal. That's the 1OH, so it looks like this. There's an R, an H, and it can also have an R group, by the way. OH and OR. So you're halfway there. But all the way there means that you kept reacting it and you got the full acetal. OR, OR. So geminal ether is an acetal, right? Geminal diether, I guess I should say. And then you had an aldehyde or ketone to start. So those are pretty important. Let's see how they look with some other reactions. Now, I'm picking a special looking diol as my nucleophile. All right, so this is kind of important because this mechanism is based on the previous one. We should be able to do this no problem. I'm still going to do it with you, but we're going to start kind of going a little faster. So we have a ketone, we have our alcohol, we have acidic conditions. The acid present is going to be this alcohol. Which one? Pick one. Protonated. Okay. And then we need to also have the ketone activated. So activate your carbonyl. So that's what we'll do first. Just in case we forgot, what I'm actually going to do to shorten this mechanism, I've shown you what the full acid looks like. And we've done this extensively in Organic 1. We're going to sometimes call this H plus if the exercise goal is not only the mechanism. If the goal of the exercise is to flesh out the whole mechanism in great detail, we've got to show how the acid was formed, what exact acid we're using, how it was deprotonated. So none of this minus H plus H plus business. We have to show the whole thing. But in this scenario, our goal is to get the product done and get the generic mechanism. And when you're trying to do that in lots of homework, it can add 5 minutes per problem to do those extra steps. And when you feel confident that you know how to do this step, just say this is a source of H plus. Okay. You've already done the full mechanism a few times. Now let's move on to the meat of it, because this acid-base stuff is kind of, we're going to assume that we know that, and it's going to get tedious if we only focus on that. So let's say we know that there's going to be H plus source, and we're just going to activate. So I'm going to write that as a reminder because we don't want to forget. So acid, therefore activate carbonyl first, right? That's the first thing you do. Now it's activated, it's hot, it's ready to be attacked. Who's going to attack? Look over your arrow. Never use tosic acid. Use the alcohol or the water that was given. Okay. Here's our alcohol. It's this funky diol that that's actually a very common one. But because it's funky, oh, you could pick either alcohol though. I'll pick this one since it's closer. Attack, open. All right, so now we're going to branch this guy out. OH here from the original oxygen, protonated here. Okay, so do you want your mechanisms to sometimes look a little shorter while you're doing homework? I think you do. I'm going to show you this, but if it makes you uncomfortable, do the entire thing until you feel ready to do this. But I am sharing this with you for whenever you are ready, okay? Because acid and base proton transfer is going to be happening throughout the rest of the class, and it can add 5 steps to an already full page mechanism. And like I said, that adds up to lots of time spent on that. So just like I'm allowing you, you're advanced enough now to do that. Wouldn't let the little 211 organic 1 newbies do this. You guys are ready. So the H+, in the same vein, I'm also going to say, grant you permission to do what's called a proton transfer. So because I've done this mechanism before the full way, I'm going to show you the shortcut that's actually accepted in literature, because even if you're reading a scientific paper, you don't want to read baby acid base steps. You want to get to the meat of what's new or interesting that happened, right? So proton transfer. What am I trying to do with proton transfer? I'm trying to say, I don't want this here anymore, okay? And I know that I'm going to have this go. Why do I know that? I'm trying to form an acetal. How about I even draw this product for you? Just so we can get what our goal looks like. Acetal means 2 ethers on the same carbon, but because we use this really funky diol, they're connected. That's our goal, this acetal. 2 ethers on the same carbon. With that in mind, look where I am now. I want this gone. I want this to stay. This is my 2 carbon piece here. Knowing I want this gone, I need this to turn into water and I need it to leave. How does it turn into water and leave? It needs a proton. This needs to stay, so it needs to be neutralized. These guys can help each other out. They don't literally, this doesn't literally grab this H+. What happens is something neutralizes this, then then we draw the new product, then something comes along and protonates that, then we get the water to leave. We're going to skip those separate steps and just say, hey, we know there's all kinds of transfer from side to side. What we're going to do is instead just acknowledge that by saying proton transfer ultimately to where we need it to go. So that means we're going to let the thing that we want to leave as water get the proton. And the thing we wanted to neutralize, ditch the proton. Okay, so let's even track that, just because it's our first time doing that shortcut. Here's our proton transfer. It's here now. There are no arrows for proton transfer, because proton transfer is condensing several steps. What is it condensing? We've done this before, right here. So notice here, if we wanted to get to the acetal, we could have skipped all of these steps all the way to here by doing proton transfer. We could have said, okay, let this one go to here by proton transfer. So I'm going to write that here, just if you want to go back and add it. Or H plus transfer. What does that mean? The thing I wanted to neutralize is neutral. The thing I wanted to protonate is protonated. Just one proton. I'm not allowed to draw arrows in the blue path because the blue path represents a shortcut for several arrows drawn in several separate paths. So it's like when you say tautomerize, you cannot draw arrows for when you do that as a shortcut unless you're showing every step of the tautomerization. But once you've proven you know those steps, you're ready to kind of upgrade and say, hey, I want to get to the meat of the mechanism. I won't want to show a series of acid-base protonations, which was chapter 3 or whatever. We're in the, big kids playground now, as my kids would say. That's the important thing, the big kids playground. And so we're in the big kids playground of organic chemistry. So we're not doing the baby stuff anymore. All right, so proton transfer means we are acknowledging this came off, went somewhere else, and then it ultimately ended up here. Okay? So no arrows to draw. Feel free to take your time with it though. Okay, you don't have to do it if you like doing the whole mechanism. So what's nice about this is we're ready to eject. The reason we did the proton transfer is to make a leaving group out of that water. We don't want it there anymore. We know we don't want it anymore because we're trying to make an acetal. Acetals don't have any OHs. Okay, so let's close that up. Use your lone pairs to eject it as a carbonyl, thus in turn activating the new carbonyl so that it's ready and happy to be attacked again. Who's going to attack it? This guy. Instead of having a new OH or OR H come in, you're going to do an internal attack. Remember, intramolecular happens before intermolecular. Write that down, intramolecular attack. Intra, because it's already there, it's the proximity. Molecular happens before intermolecular. Intra means it's part of the molecule, inter means it's between two molecules. So another alcohol is not going to come along because this was a diol. It had a second alcohol ready to go and it's already attached. So it's going to come around and attack. Open. Now what does that look like? Let's number. We're attacking here, starting with this. This is going to be part of the ring since we're closing the loop. 1, 2, 3, 4. And then we stop here because this is where it attacked. 5. 5-membered ring. So 5-membered ring, spiro connection, sharing a carbon. So in other words, that carbon right here has 2 groups coming off of it now instead of 1 that are part of the ring system. Okay, so O, O, and then remember the bottom O that was 1. Let's keep our numbers up just so we can 5, 4, 3, 2, 1. Oxygen number 1 still has its hydrogen attached. And you can show that deprotonation, but like I said, we're entering the big times now where this is okay, because that's not the meat of it. The meat of it is how did we form those new bonds, not how did we transfer protons to facilitate it. All right, so that's the point of this mechanism shown the short way. This could have been the whole page if we didn't do those minus H plus shortcuts, plus H plus shortcuts. So right here, and H plus transfer shortcuts. But once again, you don't get penalized for showing the full mechanism either. Now this is acid-base, so it's actually reversible. You can take any acetal, add your H plus, and way too much water because we want to get the alcohol back. So notice there's no water in the forward direction up above. No water. We did lose water a little along the way, so there's some water. And so we do also like to show that sometimes and emphasize that with our mechanism. You could drive it off with a little curved arrow coming off, like a little byproduct. Okay, so to go backwards, we can though, make our ketone. Plus the diol. Okay, so this equilibrium is illustrated and summarized in this chart with acetals, hydrates, hemiacetals. And you're going to notice another term that sometimes comes up. one textbook, Klein, he does not distinguish between hemiacetals or hemiketals, acetals and ketals, but a lot of other sources do. It's kind of an old school sort of thing. So I will do it just for clarity, because I always did. It turns out that if you start with a ketone, some that are real finicky about these phrases, they don't like to call the final geminal diether an acetal, they like to call it a ketal. I was kind of raised doing that myself, but I'm trying to be flexible because I'm noticing that they're trying to simplify it and consolidate. But later biochemistry books actually often distinguish between them more, which is why I feel like we still probably should. So it's actually a ketal specific to be more precise, but you will see acetal interchangeable with ketal. So in other words, you're not allowed to use ketal for the aldehyde version. What does that look like here? If you started with a ketone, let's track them all. I'll do it in color coding. Let's do an aldehyde in green. So that's if you started with H attached. Let's say you had the ketone, I'll do it in red. No matter what you have, if you're adding water, you get the hydrate. And that's a, oops, that's a geminal diol. However, this is where it starts to look different. If you add alcohol, so notice here we added water. If you add alcohol instead, we could get R or an H with the OH. So we get one of each. Then we get the hemi, ether and alcohol, paired with two R groups means we have a hemiketal. One R group with one H means we have a hemiacetal. So let's underline that again. Acetal means there was an H there. Ketal means there's an R there. So it just means it came from an aldehyde or ketone. Came from an aldehyde, more specifically it's an acetal. Came from a ketone, it was a ketal. Okay, so these are extremely useful in synthesis because they're reversible. So let me show you. Let's get to the big time fun applications now. Okay. We are going to compare two synthetic routes. So one takes has an ester and a ketone and converts it to a ketone and an alcohol. Notice this does the same. And there's an ester and a ketone, it converts it to a ketone and an alcohol, an alcohol and an ester. So in each case, what's different is that this ketone only reacted, not the ester. So just something to keep in mind. So ketones versus esters. So what's different about them is we have this group here. Which one's a stronger electron donating group? The OR, right? Which means if we draw the delta plus on that carbon, it's tiny compared to this one. And I'm exaggerating it, of course, just to make a point. So who's more reactive? Therefore, ketones are more reactive, much more reactive than esters. So that means if we want, it's actually not many steps. If we want to reduce, so this is a reduction. We took away a bond to oxygen and replaced it with a bond to hydrogen, right? So there's a new H here. If we wanted to reduce, we just need a reducing agent. And we're going to learn that sodium borohydride, that's in our chart in the beginning, will add an H across the carbonyl pi bond, an H to each part of each of those atoms. So new H here, new H here. Sodium borohydride will do that. And that's usually in the presence of ethanol. Just do only enough to react with one of them. It won't even touch the ester. So reduces ketone first because sodium borohydride is a mild reducing agent. We'll get to that later. So it's not reactive enough for esters anyway. Okay, so that's not a problem. What does that have to do with acetals? If we wanted the reverse to happen, let's say, hey, we want to keep that ketone. We want the ester to be reduced. That's the goal in this one. We want to reduce ester. But, problem. Ketones are more reactive than esters. So if we put a reducing agent in there, it's going to go straight for the ketone and way before it touches the ester. Solution. We're going to use a protecting group. We're going to protect our precious ketone. So protecting groups are very common. We abbreviate them PG. And it's like a little mask. To mask, to disguise our ketone, and then unmask it to get it back. So who can protect it? Well, we just learned that acetals are reversible. And if we only add one, it will react with only the ketone over the ester. So let's do our little funky diol here. This ethylene glycol is what it's called. One equivalent only to make sure that it only touches the ketone, the more reactive functional group. Throw in our tosic acid. We're not doing mechanisms here, we're doing synthesis. Here we go. We get our ketal, which is a protected ketone. Looks like a little alien, right? Okay, left that ester alone like we wanted. Now we could reduce our ester. Something that reduces esters quite nicely, which we'll spend some more time on later, is LAH, as in our little summary table at the beginning, followed by a water workup. All right, here we go. Reduce it to the alcohol. We're getting there. Time to unmask. Extra water in our acid, deprotection. So deprotect, and this is called protect. So our goal was never to have the acetal show up in the end. It was just in there in the intermediate as a protecting group. That's very powerful strategy for doing synthesis. Okay, so I'm going to stop there, practice these, try this page just to see if you can do an intramolecular attack before we move on, okay? Welcome back. So this is my answer. Did it match yours? So something about intramolecular reactions I think are so fun. Remember, intramolecular happens faster than intermolecular. So notice the intra. So always do intra before inter. In other words, it likes itself more than it likes its neighbor if possible. When will that happen? When will we ever have intramolecular reactions? Notice the title of this one's intramolecular hemiacetal formation. We did indeed form hemiacetal. Notice what's going on here. We have an OR, a carbon with an OR, and an OH on the same carbon. So we formed a hemiacetal. All right, so how did we do that, and how did we know that that could happen? Well, in order for an intramolecular reaction to occur, you need to have a nucleophile and an electrophile in the same molecule. It has to be attracted to itself, in other words. So if we look at our molecule here, we have an alcohol and we have a carbonyl. What have we learned about carbonyls? We learned that carbonyls are great electrophiles. And we know that alcohols can serve as nucleophiles. All right, so nucleophile, and we have an electrophile. And just to facilitate that, notice the mild acid catalyst is not defined, so I'll just write H+. And so we activate the carbonyl, in other words. So we'll do the mechanism. Now we're going to now that it's activated, it's extra prone to nucleophilic attack. And because I'm making a ring, I like to take the time to number. And so it's worth numbering everything that's going to be in the ring. So the nucleophile is going to attack. So I'm going to start there with number 1, 2, 3, 4, 5, and I'll end on the electrophilic carbon, 6. Good. I'm going to make a 6-membered ring just like I drew in the answer, right? So we're going to figure out who's number 1 through 6. So if I draw my arrows, it should look like that. Coming around to attack, open. So I draw my 6-membered ring. But the oxygen still has the proton on it. And now I'm going to number everything before I go any further. 1, 2, 3, 4, 5, 6. Nothing else is attached to any of those other carbons except 6. So I got to worry about what's going on at 6. 6 opened up to an OH. It also had an H there. Well, look, that looks a lot like where I'm going home to. I just have to take off my H, deprotonate that positively charged oxygen. I'll just call this CB for conjugate base because we never defined the acid to begin with. So whatever that conjugate base would be, take that off. You got to be kind of flexible with it. And there we go, home free. So we could form a cyclic hemiacetal. And when these actually have a lot of significance in biochemically speaking. So our carbohydrates, for example, are based on cyclic hemiacetals and acetals. So what we actually get used to drawing those in to represent their 3-dimensional shape is going back to the way we represent 6-membered rings in 3 dimensions. So if you gave that a try, if you did this whole page, I hope that you maybe thought, well, there's actually, let me bring this back up a bit. It's actually a stereocenter here because this is prochiral. It's before a stereocenter occurs. I'm about to attack a sp2 hybridized carbon that will turn into a tetrahedral carbon. And when it does, it's going to have a stereocenter. It's going to have 4 different groups attached. So that means it really could look like this, wedged OH or dashed OH. I just didn't define which one was which. It was racemic. And what would that look like? Another way to draw that 3-dimensionally would be, you're probably hoping we got back to these. Yes, the chair conformations. As if we picked it up and kind of turned it over on its side. Oops. And but it's a chair, but oxygen's one of the atoms. So just add the oxygen in there and then draw this. Remember, chairs are 2 parallel lines. And then we have a carbon pointing up in the front and a carbon pointing down in the back. Okay. So you can, if that's my favorite chair, it's my go-to chair, if you will. We all have one, maybe. You don't have to do a chair flip because these are enantiomers. So you can draw the same chair if you want. OH, but you might want to refresh yourself on what a chair flip is. Remember, there's axial and equatorial.
I could put in my H to emphasize which one I'm drawing. Okay, so those are the enantiomers. So the reason I bring that up is because we will visit the carbohydrate unit, and chairs will come back with hemiacetals combined. So it's good to kind of see that connection right now. So we made a hemiacetal, and what this question is getting at down here is what happens if we take that hemiacetal and we do what hemiacetals do and react it with an alcohol in the presence of an acid catalyst. It should be no different than any other hemiacetal that we've reacted before. In other words, it will make an acetal. No surprise, right? So yes, we could have a cyclic acetal. So don't let the cyclic throw you off. Don't let the chairs throw you off. It's just a representation, or intramolecular throw you off. We're still in the same topic, hemiacetal, and now we have a cyclic acetal. Okay, so yes, these are all possible ways to form those products. So I hope you feel like you could redo that problem if you didn't get it and give it a go. And see you soon for the next unit, because we're going to switch gears to a different nucleophile. That's it for the oxygen nucleophiles. We're going to move on to the nitrogen nucleophiles. I'll be your oxygen. I'll be your oxygen.